Good morning, Internet. My name is Jaxie, and let's take a look at robotics large language model agent paper called ROBOGEN. In robotics, most reinforcement learning robotics are conducted in simulations that are handcrafted by humans. This enables us to get lots of data for cheap costs and being quicker than in real-world experiments. But setting up these simulations is tedious and involves designing tasks, selecting relevant and meaningful assets, generating plausible scene layout configurations, and crafting a lot of training supervisions, such as loss functions and reward. So, in response to that, the team applied generative simulation. It is a combination of simulated robotic skill learning to provide physical dexterous manipulation capabilities and large language models to provide knowledge on real-world conditions to create RoboGen. RoboGen is an automated pipeline that utilizes common sense and generative capabilities from the large language models for automatic task supervision generation that will lead to diverse robotic skill learning at large scale. Here is how it works. Firstly, task proposal. RoboGen generates diverse and high-level tasks for robots to learn. The system is initialized with a specific robot type and an object randomly sampled from a pool, which are then used as input to an LLM to perform task proposal. The large language model can generate a variety of tasks, taking into account both robot and object affordance, and can be queried to return a number of tasks that can be performed with the sample object, where each task consists of the task name, a short description of the task, and if there are any other objects that are required for the task besides the provided articulated object, and which joins or links of the articulated object the robot will need to interact with to accomplish the task. By repeatedly querying with the different sample objects and examples, RoboGen is able to generate a diverse range of manipulation and locomotion tasks concerning the relevant object affordances when needed. Secondly, scene generation. RoboGen creates scene components and configurations based on task descriptions and retrieves or generates object assets to populate the scenes. The system uses language descriptions to obtain objects, adjusts their sizes, initializes their configurations, and specifies the scene's spatial relationship, all of which contribute to creating diverse and appropriate training environments for robotic skill acquisition. Additionally, to enhance scene complexity, RoboGen queries GPT-4 for semantically relevant objects and deploys a validation process using a vision language model to ensure the suitability of retrieved asset. It can then generate assets when necessary using text-to-image and image-to-3D mesh generation models. Furthermore, for certain tasks, the RoboGen configures the initial state of articulated objects and it sets the overall scene configuration to ensure the object's proper placement and collision-free environment, and thus enabling more effective skill learning in robotics. Thirdly, training supervision generation. To acquire the skills needed for solving complex tasks, RoboGen employs a two-step process involving GPT-4. Firstly, it decomposes long horizon tasks into shorter horizon subtasks, which can be effectively solved using existing algorithms like reinforcement learning, motion planning, or trajectory optimization. Then RoboGen uses GPT-4 to select the appropriate learning algorithm for each subtask, and considering factors such as task type, context richness, interaction complexity, and it provides reward functions and action space suggestions to further facilitate the learning process. Lastly, skill learning. The process for teaching a robot skill involves obtaining the necessary task information, scene components, and configurations, followed by decomposing the task and providing training instructions for subtasks. Different techniques are employed for skill learning, such as reinforcement learning, evolution learning, strategy, and motion planning. All of these are chosen based on the task type. For object manipulation, SAC is used as the reinforcement learning algorithm, while for locomotion, the cross-entropy method is used. And additionally, gradient-based trajectory optimization is used for soft body manipulation tasks with guidance from a differential simulator. RoboGen is generic and it is agnostic to specific simulation platforms. In this case, the team used Genesis as a simulation platform for deploying RoboGen, and they use SAC as the reinforcement learning algorithm for RoboGen. And now let's take a look at some of the results. In assessing task diversity, many aspects need to be considered, including semantic meanings, scene configurations, object assets, and robot actions. So, to measure the diversity of semantic meanings, quantitative evaluations were conducted using self-blue and embedding similarity scores, with lower scores indicating greater diversity. The comparison involves established benchmarks like RL Bench, Maniscale 2, MetaWorld, and Behavior 100. The results, as shown on the table, reveal that RoboGen outperforms previous benchmarks in terms of self-blue and embedding similarity, highlighting its ability to generate highly diverse tasks that rival or surpasses manual human-crafted skill learning benchmarks. Next, in assessing scene validity, they employed Blip2 scores to measure the alignment between the rendered object images and text descriptions within the simulation. They examined two types of ablations. Number one, omitting object verification, where objects are retrieved solely based on the text matching. And number two, removing size verification, substituting GPT-4's output with default asset sizes from object words or partnet mobility. And as the figure shows to us, it illustrates that Blip2 scores for these methods across 7 example tasks, and it highlights the substantial decline in score when the size verification is absent, underscoring the disparities between default asset sizes and real-world dimensions. Additionally, no object verification results in lower Blip2 scores with greater variances, emphasizing the enhanced object selection validity achieved through our verification process, thus affirming the significance of object and size verification in RoboGen. And not only that, they also assess the efficacy of training supervision validity through qualitative evaluations, by using the image and videos showcasing the learned skills employing generated decomposition and training supervisions. So, in figure 3 on the slide, the skills acquired using RoboGen's training supervisions, including task decomposition and reward functions, are illustrated across four long horizon tasks. These demonstrations reveal the robot's successful acquisition of skills necessary to accomplish the task, indicating the effectiveness of automatically generating training supervisions in deriving practical and meaningful abilities. In the skill learning performance assessment, they conducted another ablation study by excluding the options of motion planning based primitives and gradient based trajectory optimization, relying solely on reinforcement learning for skill acquisition. Each of these methods was tested with four different seeds, and they reported the mean and the standard deviation of the task returns after confirming the correctness of GPT-4 generated reward functions for the evaluated tasks. The evaluation has four tasks involving interactions with articulated objects with the results summarized in the table. They observed that the ability to select the learning algorithm improved task completion performance significantly, as relying solely on reinforcement learning led to complete failure in acquiring skills for most tasks. And finally, in their qualitative system evaluations, they showcase over 100 learned skills through videos on their website and include snapshots of representative skills in the paper. These two figures on the slide illustrate different types of tasks and skills generated by RoboGen. And this demonstrates its versatility in creating tasks for skill acquisition, including object manipulation, object locomotion, soft body manipulation, and so on. It also highlights RoboGen's ability to generate long horizon manipulation skills with effective decompositions. Anyway, that is all, folks. Thanks for watching, and don't forget to like, comment, and subscribe, and I will catch you all in the next one. Cheers.